Hi, I'm Ryan Baker, and this is Big Data in Education. Today we're going to wrap up our Knowledge Inference Week by talking about hybrid approaches to fitting Q matrices and other structures. So, how do we get a skill item mapping? As you may recall from last lecture, there's three approaches basically: hand development and refinement, automatic model discovery, and hybrid approaches. And today we're going to talk about hybrid approaches, which, not surprisingly, combine some aspects of both of these. The most popular hybrid approach is called learning factors analysis, and it's by Hao Sen, Ken Katinger, and Brian Junker. Learning factors analysis uses a mathematical model similar to performance factors analysis. It actually came first. It adds a student parameter, which is useful because it helps you fit the data better, and we actually don't care about using this in real time because we're trying to refine our knowledge structure. It also has only one learning parameter per skill, as opposed to both a parameter for learning when you fail and a parameter for learning when you succeed. So what LFA does is take an existing skill item mapping and add a set of potential candidate learning factors. It repeatedly tries to split skills based on those learning factors using a search space algorithm that goes through a lot of possible combinations. And what it basically does is repeatedly says, you've got a skill A, you've got a learning factor B. Let's try a new skill, A and B. And let's try another new skill, A and not B. Do either of these ones make the model better? And it tries a bunch of combinations of these and eventually comes to a better combination of skill item mappings, hopefully. So, in these last two lectures, I've talked about three ways to improve skill item mappings: hand development and refinement, automatic model discovery, and hybrid approaches which take an existing human-built model and try to improve it. Why is this important? Why do we actually care about this anyways? Well, a good skill item mapping is a prerequisite to using algorithms like BKT and PFA. If you consider irrelevant evidence, like student performance at hockey while predicting math, you're going to have ineffective prediction. So knowing what skills go with what items will really help you better predict student performance. It also helps you understand your domain better, and that can be useful in its own right. There's a limitation of Q matrices, however. We've been talking about Q matrices up to this point for skill item mappings, and that's that Q matrices assume no relationship between skills, except that a specific item can involve multiple skills. But if you have two skills, aside from the fact that an item can have both, they have nothing to do with each other.
And this is definitely a limitation because there are several ways that skills can interconnect. And models that represent the interconnections between skills are usually referred to as knowledge graphs or knowledge spaces.
Now, one approach that gets past this limitation is partial order knowledge spaces. Partial order knowledge spaces, or POCs, postulates relationships between items wherein the mastery of one item is prerequisite to the mastery of another item. In other words, in order to master A, you first have to master B. In order to master multiplication, you first have to master addition. Now let's look at an example, and this is drawn from Desmarais et al. You have four items, A, B, C, and D. First, let's look at B and C. There are no arrows between B and C, so B tells us nothing about C. They're totally unrelated. But C has an arrow to D. So if a student succeeds at C, they will succeed at D as well, which means that D is prerequisite to C. If knowing C means you get D, then it must be that you had to know D to get to C. Is that clear? So basically, every item can have prerequisite items. Now, POCs can be extended rather easily to use skills, interchangeable items, rather than items. And that's why we're talking about it here. So you can think about skills that have prerequisite skills. And this kind of work goes back all the way to Gagne in the 50s and 60s. There's modern versions of it in today's learning analytics and educational data mining, but this is an old topic. Bayesian networks are another framework you can think about. They're a less restricted set of models that also infer relationships between skills and items and between skills. A lot of things are simple versions of Bayesian networks. For example, BKT and every advanced BKT model we talked about was a very simple BayesNet. But BayesNets can be much more complicated as well. They can infer very complicated relationships between material compared to a skill item mapping or the very restricted set of relationships that POCs models. So they can infer skill-item, skill-skill, item-item relationships at the same time, and multiple types of these relationships. They can model hierarchies of skills, and they can model meta-skills, where multiple skills combine into a single skill, such as all the various skills of subtraction unifying into subtraction. And they can integrate very diverse types of information. That extra flexibility is very powerful, but it can also lead to overfitting. The sheer ability to model a ton of things means you can overfit to the noise in your data. Just want to quickly show a few things that BayesNet's been used for. Won't go into all the math today. But for example, Martin and Van Lane used a BayesNet to say, if we have the chapters in a physics text, what are the concepts in those chapters, and what are the equations that build up to those concepts? Kanadi et al. Actually used a Bayes net to map between very different types of data, where she looked at survey data on students' personality traits and on their goals, the connections between those personality traits and goals, the connections between those in turn and the students' interaction patterns within a game, and the connections between those to individual action outcomes. So she linked some very disparate data together in one model. And finally, Valerie Schutt and her colleagues looked at all the factors that lead to success in a video game. And they broke it down to cognitive factors and non-cognitive factors, into things like attention, domain knowledge, problem solving, and finally down to things like working memory and such. And as they modeled specific components in this greater model, they could map up to what would eventually lead to success in Oblivion. Now, the math behind Bayes nets can be relatively complex. There are several algorithms that people use for propagating information around a Bayes net. The big idea is that if we know that a student has skill A, then this provides us with information about all that skill's prerequisite skills, and some information for skills for which skill A is itself a prerequisite, and some information about relevant meta skills. Anytime there's a connection in a Bayes net, information can travel across it. So one question you might want to ask yourself is, should I be using a Bayes net? Should I learn about this? Or should I use one of the simpler models that Baker's talked about in this class? And the big question is, how much do the interconnections between your skills matter in the context of your learning system? And how much do you care about the hierarchy of skills? The cost of a Bayes net is complexity, overfitting, and overpropagation of information. The power of a Bayes net is it can fit very complex structures that the simpler models simply can't fit. Some online learning systems that are quite popular use Bayes nets, like ALEX. Others use things like Bayesian knowledge tracing, like cognitive tutors. Which one you use kind of depends on what your needs are and the design of your system. So there's a couple tools for creating Bayes nets. I actually asked a couple of colleagues who do this more often, Valerie Schutt and Russell Allman, and they recommended Netica and SamIam. There's also apparently an extension of Netica for use in the R package, for those of you who are R followers out there.
So let's talk for a minute about how this sort of thing is used in the real world. First of all, every learning system that uses a knowledge tracing algorithm like BKT or PFA is going to need a Q matrix. You can really only dispense with that need if you're using an uninterpretable algorithm that just predicts immediate performance, like deep knowledge tracing, for example. Second of all, many learning systems use a knowledge graph to decide, for instance, what prerequisite skill support to give a struggling student, or to assign a student new content based on what he or she is ready to learn. And there are real-world benefits to refining skill mappings. For example, when people have tried to improve skill item mappings using LFA, it's led to better prediction of new students' performance in 10 of 11 real-world datasets. But even more importantly, the newly discovered skills that came out of this process led to tutor redesigns that in turn led to better learning for students. So there's a real benefit to getting these skill mappings better. And beyond this, there's evidence that there are benefits to using a knowledge graph to assign students what to work on next. 2 papers have found that if teachers assign students content that the system thinks the students are ready to learn, according to the knowledge graph, these students will perform better than students who are assigned content that they're not yet ready to learn, that there's some skill they still haven't learned in between their current knowledge state and the skill they're currently learning. So that's it for Bayes nets. Next up, a deep dive into learning curves, what you can tell just by looking at them.